So the second type of flow that we can have is earth flow. So remember that we had creep, now earth flow. So the earth flow is going to be slow to rapid downslope movement of water saturated soil, and debris moves as a fluid, kind of. So the earth flow moves similar to what slumps or slides kind of do. It moves sort of as a semi-consolidated block, but it is a little bit more liquid, and so it's going to move inside as well a little bit more than just the block moving downwards from a plane or a curved plane. So it's going to move, yes, as a non-consolidated block, but within the block there's going to be movement also. So you're seeing here two different examples of it. You're seeing that obviously it's not incredibly big, either one, but you're seeing that it looks kind of fluid. It has this hummocky terrain kind of look to it, but it's not incredibly fast either. Okay, the third type of flow that we have is going to be debris flows or mud flows, which are pretty cool, obviously devastating, but very cool. So they're very fast. They're between 5 to 80 kilometers an hour, which is somewhere between 3 and like 50, 55 miles an hour. So debris flows are going to have up to boulder-sized particles that are supported in this kind of water slurry. So the reason why you have these boulders inside of this kind of water slurry, why they travel and not just simply sink to the bottom, is because this water slurry has a fairly high viscosity. So if you guys remember our lecture on volcanoes, we talked about viscosities somewhat. And so higher viscosities usually tend to flow slower and then, higher viscosities, flow slower, and then lower viscosities flow faster. So something like water flows very fast because it's not very liquid, but if something like honey flows fairly slow because it's more viscous. And so this water slurries, because they contain a lot of mud particles, mud-sized particles, clays and silts, I should say, it makes it fairly viscous. And so because of that viscosity, it's able to kind of withstand the weight of the boulders, at least for a little bit, in order to carry them downwards a little bit. So both the viscosity and obviously the gravity that is pulling the boulders down are able to move the boulders, it could be meters, it could be kilometers away from the source. So they're pretty cool, and we'll look at a few examples in a second. And then mud flows are going to be debris mixed with water with a high proportion of mud. So the mud flow is basically the debris flow without the very large sized particles. So in the picture on the right, if you guys remember, this is a mud flow or a lahar that is a consequence of a volcanic eruption. And this particular one is in Armero, Colombia, I think. Actually, no, this one is in Venezuela, if I'm not wrong. So you can look it up. It's actually pretty cool. But anyways, so here's a few examples of the debris flow sediments or deposits. So you see right here on the left image that you have a bunch of very fine sediments. So that's all that water slurry remains. And then on the sides, for the most part, you have these big boulders that were pushed out of the way by the rest of the debris. So here you're seeing a mix between the big boulders and finer sediments that made up that water slurry. And you'll see how that kind of forms in a second when I play that video. Let me see. So I'll play the video for that so you can sort of see. So I want you to keep an eye on the boulders. See how they're all moving on top of the flow, and they're being pushed kind of to the sides for the rest of the flow to come through, because the boulders are very heavy, so they don't want to be carried. So they're pushed to the side, but at first they're all flowing on top of it. Very cool. Okay. So again, those are going to be the debris flow deposits. And then mud flow deposits, we get this very yucky, slurry thing that eventually becomes just mud-sized particles once the water either leaves or becomes kind of consolidated within. So I'll show you now a mud flow. This is actually kind of debris and mud flow experience. So this is in Aconcagua, in a volcano. Aconcagua is a volcano up in the Andes in Argentina. So they spell a few things wrong if you know Spanish, so I apologize in advance. But the video is very cool. So you see that they're just hiking. I think they're all geologists, so they should have a fair idea of what's going on. Right now there's just spring runoff going through, but they're just hiking along this area. And you see that they're hiking on top of what was probably a lahar deposit beforehand. So you see that in the previous little image that they showed, there was very fine sediment along with some bigger rocks. Okay. Crazy. So you see that right now, that's a debris flow carrying some big boulders down. Poor people. And then you see that it becomes a little bit just more muddy as it goes downhill. Less boulders are carried along. There's probably less particulates to be carried anyways. But anyways, that's a very fast one. Obviously the slope of the volcano has a big effect on how fast that is. Also, there's no vegetation to kind of slow it down. So those are those forces taking, place. Anyways, very cool. Okay. Let's see. Fourth type of flow that we have, I think it's the fourth, is going to be an avalanche. So in this case, avalanches are the most rapid type of flow. Remember that debris flow and mud flow are, 50 or 50 some miles an hour at most. These guys are 100 feet per second, so per hour. Let me do the math real fast. So per hour they'd be moving, what is this? Say 360,000 miles an hour. No, that's feet an hour. I was gonna say that's insane. But they are moving over 70 miles an hour, so very fast. There you go. And so with avalanches, if you're from Idaho, you might be a little bit more familiar with them, or at least with the remains that they cause, what they cause overall in the landscape. But with an avalanche, you're going to have things moving downward, such as snow, ice, and whatever is on their path. So many times you see that trees and rocks also move with avalanches, or people, if they're skiing, you see many news with people that have died in avalanches, unfortunately, because, we are propense to it. And with moisture, there is even more capacity for them to happen. So you're seeing here a few classic images of avalanches, and then on the left hand picture you're seeing the remains of what an avalanche caused after it went through the area. So you see a lot of torn up trees, little boulders displaced every now and then, and it can cause a lot of burial, obviously, by snow or ice. So if it's sort of early in the year, it can take a lot of money to kind of clear up roads or houses or whatever it may be that the snow and the ice fell on top of. Two different type of snow avalanches, or just avalanches, I guess I should say. So the first one is going to be loose snow avalanches. So they start out in this very kind of narrow chutes, if you would, very small, and as they get downward, picking up all the material, they widen downslope. And then they tend not to be super dangerous, but depending on the beginning stages of them, they also could be very damaging. But then we also have slab avalanches. So they move more cohesively. They move a little bit more kind of like slumps and slides. So you can think of um, the overall block that is moving as the more recent snowfall event, and that the boundary in between two different snowfall events is going to be the boundary on top of which the avalanche sliding block is moving downwards. The flow block is moving downwards. So they tend to be more dangerous and more damaging than the loose snow avalanches, because anything that is triggered along any part of this kind of weakened area where it might occur is going to cause anything along that area to go downwards as well. So it's not like if you trigger something here, only this part is going to come down, but the whole thing is going to come down. However, in the loose snow avalanches, because they start out kind of small, they're not going to affect, say, if I start it here, they're not going to affect whatever might be falling up here. So the slab avalanches tend to be a little bit more dangerous. And so they can be triggered by the overloading of that slope. So if I have way too much snow on a particular snowfall event on top of other snowfall or other snow that has, that fell in previous events, and I just cannot hold any more weight on top of that slope because of the angle of the slope perhaps, then that's going to be too much weight, and so it's going to trigger that slope to let go, not have enough strength to hold all that snow, so it's going to let go, and the snow is going to fall into this flow. Yeah, so those are two different types of avalanches: loose snow avalanches and then the slab avalanches. So this is another type of landslide, and geologists pretty much just called it complex because it had a bunch of different landslide kind of qualities to it. So as you can see, it's a combination of slides, slumps, and flows. So it's something where everything is occurring, maybe at different parts of that slope, but everything seems to be occurring due to the different materials, the different angle, probably different saturation as well. And so in this complex type of landslides, you can get anything. And this is one of those kind of similar to the Oslo landslide that you saw not too long ago, where we had probably a slide and a slump, and maybe at the bottom we even had a little bit of a flow, or it has happened as flows before. Same thing can happen in this picture that you're seeing on the right, for example. You see that on the top, this almost looks like it's kind of like an earth flow. It looks a little bit liquidy. But you also see some headscarps over here, which could indicate either a slump or a slide, probably a slump in the kind of like curved surface rotation underneath. And then you see kind of like a slide over here at the bottom, where the whole block just separated and is flowing downwards together cohesively. So again, complex landslides is a different kind. Done talking about the types of slides, but now if we want to understand how is it that we have the formation of these landslides to occur, we need to talk about the different forces on each slope, or on the slopes, and how the forces in them and the magnitude of each force is going to affect whether or not I have a landslide. So the driving forces are going to be the forces that are moving the materials down slopes. Okay, driving forces are actually causing the landslide. And the main force, the main driving force, is going to be the weight of that slope material. So in this case, as the picture is kind of showing, this rocks and the soil are on top of the slope, and if there was subsequent, say, rockfall from this cliff over here onto the slope, it may be too much weight so that the whole slope would kind of weaken, and there may be a slide or a flow or a slump to occur in that particular slope. So again, driving forces are those that move materials down slope. The main driving force is going to be the weight of that slope material.